We are very happy to have Aditya Hebbar from EPFL, and today he's going to tell us about spinning S matrix bootstrap in coding. Over to you.
Yeah, thank you for the opportunity to talk. So I'll be talking about the spinning S matrix bootstrap, and this is based on this paper that we put out last year with Dennis and Joao. So basically, the outline of the talk is I'll give an introduction and then I'll talk about the scalar S matrix bootstrap. So I'll just do a recap of this, which was work done around 3 years ago, so this work is basically a generalization of the scalar S matrix bootstrap, which I'll describe now soon, to particles with spin. So the main idea of our paper was to set up the formalism to consider scattering and bootstrapping the scattering of particles with any spin and mass. And then, so in this talk, I will basically describe that. And then as an application, we also consider the next step up from scalar scattering of scalars, which is basically identical Majorana fermions. So this is the simplest thing you can do once you add spin. And I'll basically show how we can apply the formalism to this special case and show some plots and some bounds that we got for this case. So non-perturbative bounds. And then I'll conclude with some outlook and what kind of future prospects are possible. So what is the S matrix bootstrap? So basically the idea is that we would just like to use the analyticity, the crossing and unitarity of the scattering amplitude to constrain the space of QFTs. And actually this idea is quite old. So it was actually tried in the 60s. But the modern revival was inspired by the success of the conformal bootstrap, where basically the analyticity, crossing and unitarity of the conformal correlators are used to bound, say, operator dimensions and OPE coefficients. And I guess all of you might have seen this plot where this famous plot where this island of allowed region, this allowed island is plotted, and the dimensions are much smaller than what you can get through Monte Carlo, for example. And this was basically the inspiration for the modern revival of the S matrix bootstrap, which I will describe briefly now. So actually the S matrix bootstrap in its modern form has been quite successful already in 2D. So what I mean by that is that the idea of the S matrix bootstrap, as I mentioned, was to plot this allowed space of QFTs. And it turns out that in 2D at least, known integrable theories were found on the boundary of this allowed space. So in some sense, they are extremal. In 4D, however, this has not been the case till now. So there is some allowed space of QFTs, but there is no known QFT on the boundary. So there is some sense in which you can say that, okay, we are not applying all the constraints, or so there is something more to be done. Another fact about S matrix bootstrap in 4D is that all prior works dealt with scalars, possibly with global spin, but with the external particles were always scalars. So in our work, the idea is to generalize to spinning particles, and this would allow studying more phenomenologically interesting cases such as pion-nucleon scattering or maybe spinning glue ball scattering, and then we could compare it to lattice or to experiment.
Sorry, Aditya.
Yeah.
So in the first point, you're referring to the Sine-Gordon model, or you have more examples?
Yeah, I think they found, Sine-Gordon model, and then I think they found some SUSY versions of that also. I think there were some ON models also that they found. So this, do you know this paper by Pedro Vieira and Krushenski and Lucia Cordova?
I see. I should look at it now.
Yeah, I think they looked at this ON models, and they also found some things under boundary there. But yeah, in 2D, I think there are quite a few examples, if I'm not mistaken.
Also, the things with rational S matrix or just the trigonometric, because the integrable models have this classification of rational trigonometric.
Yeah, this I'm not too sure actually. Yeah.
Okay, thank you.
Okay, so now I'll just give a brief recap of scalar S matrix bootstrap. So basically we want to consider 2-to-2 scattering of identical scalar particles. So basically you have two incoming scalar particles, two outgoing scalar particles, and then the amplitude is the element of the scattering operator in between these states. We separate out this identity piece, which is just free propagation. And then that's the momentum conservation. And once you do that, what is left over is a function of the Mandelstam invariants, as these are called, ST and U, and they are defined as some inner products of the momenta. So S is basically the square of the center of mass energy. T and U are basically called momentum transfers. And there are three variables defined here, but actually there is a relation that S plus T plus U is 4m squared. So actually only two of them are independent. So this is the definition of the scattering amplitude. And it has the so since we consider scattering of identical scalar particles, if you cross the process, it's the same because so it's a neutral scalar. Yeah. So if it's when you cross, it goes back to itself. So the S, T, and U channel processes are all the same, which means that under crossing, the function goes back to itself, which is basically saying that this function is totally symmetric under interchange of this argument. So it's a constraint on the amplitude. For analyticity, what was assumed was something called Landau analyticity, which says that you for the non-perturbative amplitude, you assume the same analytic structure as what you would find in perturbation theory to all orders. So you look at perturbation theory diagrams, see where you would find these non-analyticities, and then you say that the non-perturbative amplitude also has the same analytic structure in the ST and U planes. And more precisely, if you consider this particle being scattered to be the lightest particle, then the only possible non-analyticities are bound states between 0 and 4m squared, and multi-particle cuts that can start from 4m squared. But actually here, this bound state, for example, since the particle we are scattering is the lightest, this bound state can't be lighter than that. So it's actually between m square and 4m squared. But yeah, other than that, we don't expect any other kind of non-analyticity in the ST and U planes. And finally, unitarity says that if you consider partial waves, so you take the scattering amplitude and you integrate it with this Legendre polynomial weight, and then the partial amplitude defined as here have to have unit modulus for any positive integer spin and energy greater than 4m squared. So this is the unitarity constraint. So these are the properties of the scattering amplitude. And the idea of the scalar S matrix bootstrap from 3 years ago in 2017, was that we first write an ansatz which is manifestly crossing symmetric and which has the right analyticity properties. So you have the amplitude and you write it in terms of some functions. So here alpha are the coefficients, and f are some functions which I'll describe maybe later. I will describe later. But the key point about these functions is that they are crossing symmetric and they have the right analyticity structure. And these alpha are the coefficients. And then unitarity, which says that these partial waves that I defined in the previous slide have modulus less than 1. You can write it in this matrix form, which has the benefit that it is now linear in these coefficients alpha. So you can implement it as a semi-definite positivity constraint, and you can use it to it in this program called STPB, for example.
One question.
Yeah.
So, I mean, on this partial waves, there is also a constraint on the imaginary part, right? That the imaginary part should be positive.
Yeah, but this constraint takes care of both. As in the imaginary part being positive comes from this, because if you write this as 1 plus I times t, then it tells you that the imaginary part should be positive, and also that it's bounded, like the modulus of t should be bounded by imaginary part. So you get both from this.
Oh, I'm sorry, you have included 1 here. I see.
Yeah, here.
I see, but the okay. I see. So the imaginary part that I say that it should be positive is the stuff that multiplies I, right?
Yeah, exactly. So if you remove this 1 and remove this I, then this thing that I've defined here, so this, if you could call this a TL, like the partial wave of the T operator. Yeah, that should have positive imaginary part. Yeah, but that follows, like if you just plug it in there, it will follow, because the 1 will cancel and then it will follow from there.
I see. So SL is modulus of SL is less than equal to 1, has all the constraints.
Yeah, it has the full constraint. Yeah.
I see. Thank you.
I mean, this is basically the state. So unitarity, you can think, is basically the statement that S dagger S should be identity, right? And then if you write, basically this just comes from that.
Right. And it's less than 1, less than equal to 1, because there could be some inelasticity.
Yeah, exactly. So it's equal to 1 if you didn't have any other out states to go into, but in general, that's not true. It could go into, say, 4 particle states or some other particles in the theory. So it's less than equal to 1. Yeah, precisely.
Because I brought this up because, you know, some of the recent papers on the S matrix bootstrap have dealt with this stuff that multiplies, right?
Yeah, exactly. So here, since we are doing it numerically, we can just directly put this. But yeah, the recent papers, what they do is indeed they consider just this, and then they basically use the fact that imaginary part is positive. Yeah.
And the motivation to do that is because of the linearity, because the
yeah, exactly. Yeah, yeah.
Okay.
Yeah, because you see so this constraint, if you write it out, it will give you two constraints. One is linear, just that the imaginary part should be positive. But there is also another constraint that the imaginary part should, I mean, the modulus of this TL should be less than the imaginary part. So that is actually non-linear constraint.
Right.
Yeah.
Modulus squared, maybe.
Modulus squared should be less than, based on your normalization, it's twice the imaginary part, it should be less than. So that constraint is non-linear. So that's why people usually don't talk about, I mean, it's not easy to impose it in, and usually they just look at the other side.
Thank you.
Yeah. Okay, so by using this methodology that I described, these authors in 2017 were able to get some nice bounds. For example, on the cubic coupling of the two scalars being scattered to, say, a third scalar bound state, they found that the residue, which is basically the coupling, is bounded as a function of the mass of the bound state. So they found some nice bounds like this. And they also found bounds on, for example, the quartic coupling of the scalars. And so our motivation in this work is to set up the formalism to repeat this for, say, particles of any spin. And then, yeah, we will do the same for Majorana fermions. So are there any questions about the scalar case or the motivation / the idea?
So one question, is this an extremal bound? Is it known if there is a theory that saturates?
No, so that's why. So it's not, I don't think there is any, I mean, we don't know if there are any theories on the boundary. And I think, and there are some indications that, like, because in this, we only put in unitarity, but actually there is also this constraint of elastic unitarity, because between s equals 4m square and, say, 9m square or 16m square, the partial amplitude is exactly equal to 1.
You mean modulus?
In modulus, yeah, because the only thing available to the two particles is to go back to the same two particles. There's nothing else it can do. But this is not imposed. And for example, because of this, there is this result that, for example, if you consider the double discontinuity of the amplitude, it has some curve after which it can be non-zero and before which it should be 0 and things like that, and that we do not impose. So there are indications that, in fact, like the actual bounds might be stricter.
I see.
Yeah.
Thank you. Who discusses this double discontinuity and so on?
Yeah, so there was this paper by Sasha Siboedo, Miguel Correa, and Amit Sever It was I think it was called a toolkit for S matrices or something like that. But yeah, I think they discuss
Okay.
in detail. Yeah.
Thank you.
Because this stuff people actually discussed in the 60s, but yeah, this is like a modern overview, and they also discussed some more, a bit more in depth. Yeah.
Yeah, thanks.
Okay. So now we would like to generalize everything that I mean, what we described for the scalars to the case of spin. And before I get into the details, I would just like to give an overview of what changes compared to the scalar case, so that, okay, everyone gets something out of the talk. Then I'll get into the details, and then, yeah, so it'll be much more technical. But here, before that, I'll give an overview. So the first thing that changes is that because particles have spin, it's no longer just one function. So each particle has spin, and so in general, so suppose the first particle has spin J1, then you see that the helicity of the particle has 2J1 plus 1 choices. And similarly for particle 2, 3, and 4. So if you don't have any additional symmetries, you expect 2J1 plus 1 times 2J2 plus 1, 2J3 plus 1 times 2J4 plus 1 number of functions. So you have multiple scattering amplitudes. For analyticity, again, there is a slight complication. There are some singularities in the S and T planes, which are purely kinematic in nature. But the good thing is you can study them in general for any spin, and you can regularize them, by which I mean you can define new amplitudes, which are linear combinations of these amplitudes, which do not have these kinematic singularities. And then we assume Landau analyticity for the regularized amplitude. Finally, since there are multiple amplitudes, crossing is going to be a matrix equation. So the S channel process, there are many amplitudes. T channel process, there are many amplitudes. So crossing is going to be a matrix equation. And moreover, what happens is that the crossing matrix is not purely numeric. It actually depends on the Mandelstam invariant. So it's going to be matrix equation, and these are basic. This matrix itself is a function of S and T. And lastly, unitarity looks similar to the scalar case, but again, in the scalar case, this was 1, 1, and S star. But now all of these become matrices. So this one is basically the identity matrix, and these partial waves are also going to be a matrix in these different helicities. And this whole matrix is going to be positive definite. That's going to be the unitarity constraint. Are there any questions? If not, I'll go into the details of explaining each of these points.
Sorry, Aditya, what are these kinematic singularities you're talking about?
Yeah, so these, so I'll explain that in later, but basically the idea is that, so one way to think of them is that suppose you computed these amplitudes by just doing, say, perturbation theory, or just from normal Feynman diagrams. Then you need to have these polarization functions, right, to go from these correlation functions to the scattering amplitudes. And these polarization functions, if you say evaluate them, you'll see that they actually have some singularities.
Sorry, polarization is some fixed vector, right? What do you mean?
So basically what I mean is, so if you consider, say, fermions, you have these spinners, right? Like this Dirac solution, I mean, solutions to Dirac equation, like the U spinner and the V spinner.
Okay.
And if you write them in terms of, so those are functions of the momenta. And yeah, it turns out that if you write them, I mean, I think maybe it'll become clearer later because I'll explain how these come about. But
okay, fine. Also probably related. So here you are in 4 dimensions, so you are working in terms of helicities, right?
Yeah.
But in general dimensions, I would imagine you would have to work with polarization vectors.
Yeah. So this, I think here we don't consider any other dimension. We'll stick to 4 dimensions. So okay. Yeah, this prescript, I mean, everything we do uses the fact that it's 4 dimensions. Yeah.
That's
because yeah, if you went to other dimensions, so these, yeah, okay. So these helicities are basically basically what happens in 4 dimensions is that the little group is SO3. So basically that's how you get this counting and so on. So if you are in other dimensions, you would have to do it using the little group in those dimensions. I mean, you could probably do it, but probably, yeah, as you're saying, polarization vectors would be faster. Yeah.
Thank you.
Okay. So now I'll give some details about what I was talking about. So we have to start from the basics. So let's consider Poincare irreps. So as we know, the irreps of Poincare are classified by the by the Casimir, which is the p squared, and also the square of the Pauli-Lubansky vector, and their eigenvalues are basically this C and this L, and you can think of this L as the spin, and C is basically the you can think of it as the total mass if it's a multi-particle state, like the total center of mass, like the energy in the center of mass frame, or for a one particle state, it's just the mass. And in addition, you have to tell the the momentum and this helicity to fully specify the state. And under a Lorentz transformation, the C and L remain invariant because they are Casimir invariants, but the momentum changes straightforwardly. So if you do a Lorentz transformation lambda, then the momentum just transforms in as it should. But the transformation of the helicity is a bit more, is not that obvious. So basically what happens is if you do a Lorentz transformation lambda, there is a Wigner rotation element of the little group, which is SO3 for a massive state, which is associated with this Lorentz transformation. And this depends also on the momentum P. And then basically what happens is if you start with a state which has helicity lambda, it goes into a linear combination of the state, some other states with helicity lambda prime. And the coefficients are given by this Wigner matrix. And this Wigner matrix is precisely what you would find, say, in your quantum mechanics course if you consider the rotation and in the spin L representation of SO3. And that rotation in this case is going to be this Wigner rotation.
So what is L?
L is the total spin.
Okay.
Right. I mean, here I'm doing in general. When you consider one particle state, it's just going to be the spin. But if you add multi-particle state, it's the total spin.
Okay.
Yeah. And the reason why we consider this helicity basis is that when this Lorentz transformation that we do is a rotation, like a spatial rotation, this rule here simplifies, and instead of being a matrix, it just becomes a phase. Or in other words, under rotations, the helicity is invariant. And intuitively, the way to understand this is that helicity is the projection of the angular momentum to the direction of motion. And when you do a rotation, both the angular momentum and the momentum transform so that the projection remains the same. And that is why the helicity remains the same.
So will you consider only massive particles because it is SO3?
Yeah, so in this formalism, yes, we do consider only massive particles, but actually many of the final results, you can just take m to 0 and the formula still work.
Okay.
Yeah. Because the problem with massless particles is that in many cases, the S matrix is not even properly defined because of these IR divergences. So only in some cases, if the interaction of your massless particle is
the
soft,
external particles can be massless.
They can be if, for example, their interaction is soft.
Okay.
Otherwise, you still have these IR divergences.
Okay.
Yeah. Okay. And yeah, so now, so this was just general Poincare irreps. in particular, there are a special class of these called one particle states. And in that case, this variable called C can be identified with the mass of the particle. And just to create some visual distinction, we use the label J for spin of a particle, so the intrinsic spin of the particle, whereas we use L for the total spin of, say, multi-particle states. And in the previous slide, I was talking about the Lorentz transformation property. Discrete space-time symmetry. So for example, under parity, basically what happens is the momentum changes points in the opposite direction, and helicity also changes sign. And intuitively, you can understand this from the fact that under parity, the momentum is changing sign, but the angular momentum remains the same. So if you project, you pick up a minus sign. The phase you can't get from this intuitive argument. You actually have to do some algebra to fix this phase, and I won't have time to show this algebra. Similarly, for under time reversal, the momentum changes sign, but this time the angular momentum also changes direction, so that the projection remains the same, and that's why helicity is invariant under time reversal. And once again, to fix this phase, you have to do some algebra. Okay. So now now that we've reviewed one particle states, we can define the spinning scattering amplitude. So we write the S operator as 1 plus IT. So 1 is again the free propagation piece. And then we consider two particle states, which are just tensor products of one particle states. And then the scattering amplitude is just the matrix element of the T operator. So you just take T operator, and then you take matrix element in these two particle states, and you remove this momentum conserving delta function, and you get the scattering amplitude. And the Lorentz transformation property of the amplitude just follows from that of one particle state. So the incoming particles, which are kets, they transform with this Wigner-D matrix, as I reviewed in the previous slide. And the outgoing particles are brass, so they transform with conjugate of the Wigner-D matrix. So this is the Lorentz transformation property of the amplitude. And now, as you can see, these are functions of the four momenta, and they transform. So now, if you want to you can't directly write them as functions of the Mandelstam invariant. So if you want to do that, you need to do a little bit of more work. So there are basically two options to do that. So the first option is to define what are called tensor structures, and I've labeled them by this bold T here. And their job is to take care of all the Lorentz transformation property of the amplitude. So when you do a Lorentz transformation, you pick up these Wigner-D matrices. And basically what happens is these tensor structures are the ones that pick up this Wigner-D matrix, so that what's left over, the scalar components, are invariant. That's option one. Option two is that you just define your amplitude in a special frame. And usually it's done in the center of mass frame, which I'll describe next. So basically you just define that the scattering amplitude as a function of the Mandelstam invariance is just the scattering amplitude evaluated in a special frame. And then
Aditya, the TL, the scalars could also have some other Casimirs in it, right? Because
what do you mean?
Only STU, like
what other Casimirs could it have?
Like the helicity?
No, all the helicity dependence will be in these tensor structures.
Oh, there's no inner products or anything which is invariant under.
Yeah.
Okay.
Okay. And right, so these so you just evaluate them in the center of mass frame, and then in any other frame it's unambiguous, because you just use this rule to define the amplitude in any other frame. And in this in the rest of the talk, we'll mostly focus on the second option, but I'll also have something to say about the tensor structures for the special case of Majorana fermions. And for the experts in CFT, the first option is basically like the covariant frame or the embedding frame approach in CFT correlators, spinning CFT correlators, Whereas the second option is like the conformal frame approach for the spinning correlators. Okay. So what is the center of mass frame? So in a picture, it's just this. You put the first particle along the positive z-axis and the second particle along the negative z-axis. The third particle is at some angle theta, and the fourth particle is opposite the third particle, and everything is in the xz plane. In equations, it's just, yeah, the first two particles are along the z-axis. The third and fourth particles are at an angle theta in the xz plane. And yeah, so now you can basically, for any mass, you can write what these energies and the momenta are, and also the angle in terms of the Mandelstam invariants. And these formulas are cumbersome. For the equal mass case, it's much more succinct. So I'll just display that. So as you can see, the energy is related to the variable s, the momentum is related to s and m, and the angle theta is dependent on s, t, u, and m. And here, and also for and yeah, this is where you should notice that at these special points, s equals 4, s equals 0, t and u equals 0, there are some non-analyticities, and this is actually going to be the reason for kinematic singularities, which I'll discuss a bit more later. Okay. Yeah, so now we've defined this center of mass frame. We would like to discuss crossing. And first, so what is crossing? So crossing is the statement that if you take an amplitude and you analytically continue it to the complex momentum, to complex momenta, and through some path in complex momenta, you also define it for negative energy momenta, because you physically they're defined only for positive energy momenta. Then crossing says that if you say take the 1 3 bar going to 2 bar 4 amplitude and evaluate it for some negative energy momenta, then it's basically going to be the 1 2 goes to 3 4 amplitude, but the physical amplitude. And once you have spin, you see that there is a basic question that arises. So you have a list of amplitudes here and a list of amplitudes here. So under crossing, which amplitude goes to which? And historically, this was deduced by comparing Lorentz transformation properties. And there are different ways to do this analytic continuation. So for a particular choice of analytic continuation, it turns out that, so you recall that when we do a Lorentz transformation, these amplitude transform with this Wigner-D matrix, and this depends on the Lorentz transformation and also on the momenta. And now we are analytically continuing the momenta. So once you do that, this transformation, this matrix, also we can analytically continue. And it turns out that if you continue it to negative energy, it basically becomes conjugate, and also the helicity changes sign. The fact that it's conjugate is not it conjugates is not a surprise, because we know that under crossing we expect an incoming particle to become an outgoing particle and vice versa. So you expect that if you since incoming particle transforms with just the Wigner-D matrix and the outgoing particle transforms with the conjugate, you expect that when you do this, you expect a conjugate, but it also turns out that the helicity changes sign. So using this argument, we can say that under crossing, you can say that the helicity changes sign, and this is how the amplitudes are related. But under this argument does not fix for the overall phase, because in principle, if you multiply this with the minus sign, the Lorentz transformation property remains the same. So to fix this, actually, you would have to use LSZ, for example. So this gives you the crossing property of the amplitude defined as a function of the 4 momenta. But now we also, we are actually interested in the amplitudes as a function of the Mandelstam invariants. And we saw that to do that, you have to use this special frame, which is the center of mass frame. And the point is that suppose you start with center of mass frame in the S channel. Once you cross, you're no longer in the center of mass frame in the T channel. So you have to do a rotation to bring it back to the center of mass frame. And in pictures, we can do it in this manner. So we start in the S channel center of mass frame, which has particle 1 along the Z-axis, 2 along the minus z axis, and 3 and 4 at this angle. So first you do a boost, and this turns out to be complex in general, so that particles 1 and 3 are now aligned in the z axis, and particles 2 and 4 are at this angle. And now if you cross particles 2 and 3, you arrive at this configuration, which is the T-channel center of mass frame. So in equations, the first step was a Lorentz transformation. So you pick up this Wigner D matrix factors, and it turns out that throughout this whole process, you can just stay in the XZ plane, and you can just do some rotations in the Z plane, or boosts. Rotations are about the Y axis or boosts along the Z axis. And because of that, this Wigner D matrix, you don't get the full Wigner D matrix, but the small Wigner D matrix, you just get that. And in the second step, we cross, so we just have the helicities changing sign. So you can combine these two. And the key point was that we started in the S channel center of mass frame, and we end up in the T channel center of mass frame. So at the beginning and the end, they're just functions of the Mandelstam invariants. So you can combine these two, and you arrive at the final crossing equation, which is valid for particles of any spin or any mass. And the arguments of the Wigner D matrices can be computed in terms of STU and the masses. But yeah, I didn't display them here because they're quite cumbersome expression. But yeah, this is the final ST crossing equation.
Can you explain why the tensor structure thing was not so great for your study?
Yeah, so basically what happens is, if you consider, say, general spin, you can write many tensor structures, where many more than the number of independent amplitudes. Okay. And so what you would have to do is, and there will be many relations between them. So what you would have to do is to basically find out some way to choose the number of, to reduce this to an independent set. Okay, but that part is not the main hurdle, but the main hurdle is once you cross these tensor structures, you once again go out of the set, and then you have to reduce back to your independent set. So,
but
this,
sorry, go on.
Yeah, and this is so for a general prescription, this turns out to be quite complicated. And for example, one of my collaborators, Dennis Karate, was involved in doing the same thing for CFT correlators. And they found basically that this approach of using this covariant approach is more elegant, but practically it turns out to be much more complicated.
But if I give you, for example, like a basis of crossing symmetric structures, tensor structures,
yeah,
which are, say, polynomial in momenta and polarizations,
yeah,
if I give you that, then is there a problem in implementing whatever you are doing in that?
No, then I don't think there would be a problem. But you see, this already takes, so it would be an alternate way to do this. Yeah.
Thanks.
Yeah, because basically all of this stuff is actually well known from the 60s. So this is basically a review.
I understand. I just wanted to ask about so in your tensor structure, can you go back to that equation where you said option 1 and option 2, for example? Sorry.
Yeah.
So here, this on the right hand side, this that is the tensor structure, right?
Yeah. And here they're not crossing symmetric or anything. They're just generic tensor structures. So what you would have to do is cross them and then relate it back to the same basis. And yeah, if you could find some tensor structures which make that easy, then it would be convenient. But if not, also it's not too hard because you just get some matrix here then.
Right. And are there any special properties related to this, the other T, the T?
You mean this one?
Yeah.
As you mean special in what respect? So, for example, for the Majorana fermions, we do both these options. So maybe we can discuss a bit.
Maybe, yeah. Sure. Yeah.
Okay. So this was the crossing equation. And So now we took care of crossing. We come to unitarity. So before we consider unitarity, we have to introduce partial wave amplitudes. So recall that we consider two particle states. So they're just tensor products. And we always, so the center of mass frame, the two particles have the same momentum. So we can use this shorthand notation to denote this two particle state where this P is the magnitude of this momentum and theta and phi is the angular coordinate of the first particle. And lambda1 and lambda2 are the helicities of the two particles. So it's just shorthand notations to make the formula fit in one slide. And the main point is that two particle states are reducible. So you can take your two particle state and write it in terms of the Wigner-Reps that I introduced. And these are now the two particle Wigner-Reps. And the coefficients are again is this Wigner-D matrix and some phases and some normalization factor, which just depends on how you normalize your one particle state and how you normalize, your one particle state and your Wigner-Reps. In particular, we are interested in the case where the two particle states are along the z-axis and when the two particle states are at an angle theta. So then this formula just simplifies in this form. And basically, partial wave amplitudes are the matrix element of the T operator in these Wigner-Irrep states. And physically, these Wigner-Irreps are basically two particle states of a definite total spin. And once you do this, then immediately from this formula, you can write the partial wave amplitude in terms of the total, the full scattering amplitude, and it's going to be this integral with this Wigner-D matrix. For the special case where the helicities are 0 here, this reduces to the Legendre polynomial as you would expect for the scalar case. And this normalization factor I've written for the case of identical particles, but okay, you can compute this in general, but okay, I'm only displaying the simple case here.
Sorry,
so
once you say that partial wave decomposition.
Yeah.
But both have amplitude. Oh, there is an L here in the subscript. Okay. So
there's an L here.
Okay. Yeah. Yes. And what reduces to Legendre polynomial for scalars? This D.
This Wigner-D matrix, if you put 0 here, then it becomes the usual Legendre polynomial.
Okay.
Yeah.
Right. But a priori it has, sorry, what kind of object is this then?
A priori, this is like, this helicity, it's some, if you're asking if it's a polynomial in cos theta or something like that.
Yes, yes.
So it's basically a polynomial in cos theta times some, it has some sin theta over 2 and cos theta over 2 factors.
And what is the lambda 1 2? What was the lambda 1 2 3 4?
Maybe, yeah, I think perhaps I didn't. Yeah, so lambda 1 2 is the difference lambda 1 minus lambda 2, lambda 3 4 is lambda 3 minus lambda 4.
Yeah, if you have one expression for this, that would help.
Yeah, this, I think I might have it later, but yeah, it's basically lambda 1 minus lambda 2 and lambda 3 minus lambda 4. And you mean expression for the Wigner-D matrix itself? Yeah, that I think I don't have it in the slides.
Oh, okay, it's fine.
Yeah.
All right. So through the lambda dependence is only through the differences like that.
Yeah, it's only through the differences. Yeah.
Okay.
So this Wigner-D matrix is basically, as I was saying, you just consider its canonical definition is you take, say, a spin L representation of SU2, and then you do a rotation about the y-axis and take its matrix element. That's the definition.
Easy.
And this is the so if you take so that's the definition
but that's for scalars.
No, even for spin. Like you take spin L, and you take the ket to have m equal to lambda 1 2, like the jz value, and the bra to have lambda 3 4 to be the jz value. Then the matrix element of this rotation along y-axis, along y-axis is going to be this.
Right. Okay. Thank you.
Okay. So now the unitarity. So how we impose unitarity is in this form. So we consider all possible incoming two particle states like of definite spin L. So how many choices do we have? We have 2j1 plus 1 times 2j2 plus 1 choices. So particle 2 can have helicities j2, j2 minus 1 and so on up till minus j2. Similarly for particle 1. And also for outgoing states, you have these many choices. And now what is the statement of unitarity is that if you take any linear combinations of these states, it should have positive norm. And this statement is equivalent to the statement that no matter what inner product you make of these, no matter what inner product you make of these states, that matrix should be positive semi-definite, which will ensure that any linear combination of these states will have positive norm. So in equation, it's this statement that this any inner product should be positive. So you have inner products between the incoming states, inner product between the outgoing states, and inner products between the two. And the inner products between the incoming states are just going to be the normalization, similarly for the outgoing states. Whereas the inner product between in and out is going to be the S matrix element, whereas the out and in is going to be S dagger element. So basically what I mean is the diagonal entries are going to be just delta, whereas the off diagonal ones are going to be the partial waves and the conjugate of the partial waves.
Sorry, could you go back a little bit?
Yeah.
So here, just a second, this in out, this is a rectangular matrix.
Yes, if you consider some different particles going to different particles, it's going to be rectangular. And actually to be consistent, you will have to make sure that all your equations close, because you see now when you cross, you get other processes also. Right?
Sorry, what do you mean?
So basically suppose you just take some generic process 1, 2 goes to 3, 4, right?
Yeah.
If you just consider this matrix, it's not bounding all the amplitudes in your problem, because when you consider 1, 2 goes to 3, 4, by crossing, you're also required to consider the amplitude 1, 3 bar goes to 2 bar 4, right?
Right.
So you would also have to put all those states in and make like a big matrix, and that should be positive definitely.
Sorry, but if I were to look at a given process, I thought I can just focus on this matrix being positive, right, or not?
You can, but the point is you're not. I mean, numerically,
you mean
what you're doing.
Different equations. You mean there are different equations for the crossed process and so on? Is that what you're saying?
Maybe another way to explain it is that you are numerically what you're doing is that you have some function and you want to put some bounds on its boundaries, right?
Yes.
I mean, you want to put some constraints on its like on the cuts, and this will only give you like constraints on one of its boundaries. It won't give you constraints on the other boundary. So if you try to make it put some numerical constraints, I mean, make it a numerical program, it won't be feasible. So that's like a practical thing.
Okay.
I mean, but yeah, for if you just focus on one process, yeah, this is it. Yeah. I was just saying if you want to make it like.
Okay, fine.
But if you just focus on one process, yeah, yeah. Should I continue?
Yes, please. Yeah.
Okay, so that was unitarity. So this is the setup for the general case. And now we would like to apply this to the special case of identical Majorana fermions. And yeah, so why we consider Majorana fermions is related to Abhijit's question. So basically, this way the equations are the simplest. So Majorana fermions are their own antiparticles. So the cross processes are all the same. And this way we have the simplest possible generalization of scaling the scalar case.
You can do this for vectors also, like photons and such. You have done it?
Yeah, we can do it for photons also.
Okay.
In fact, that's work in progress.
So this is discussed in the paper also, photons?
No, in the paper, we don't discuss photons, but we are working on a paper right now, which will, yeah.
I see. Okay, thank you.
So let's see. So when we consider identical Majorana fermions, we start a priori with 16 amplitudes because you have 2 to the 4 number of amplitudes. We have Fermi antisymmetry. So if you interchange incoming particles and outgoing particles, the Mandelstam invariants remain the same. So it just gives you this constraint. In addition, what you can do is you can cross particles 2 and 3 and particles 1 and 4. And again, it leaves the Mandelstam invariance the same. And so you get this constraint from doing this crossing twice. And this also is because the Majorana, since it's Majorana fermion, once you cross, they are their own antiparticles. Sorry. And using these two relations, you can reduce the number of independent amplitudes to 7. And this matches the counting in 3D CFTs for Majorana fermions. In addition, we also consider parity. So as I mentioned, under parity, the helicities change sign. And what also happens is the momenta go out of the center of mass frame. So for example, the particle 1, which was along positive z-axis, starts pointing in the negative z-axis. So you also have to do a rotation to bring it back to the center of mass frame, and that process costs you this phase. And this you can compute again through some algebra, but I won't have time to go through that. So this is the constraint from parity. And if you impose this, it reduces from 7 to 5, which again matches the counting in 3D CFT. So using these relations, we choose out of the 16 possible amplitudes, these 5 as the independent amplitudes, where plus is plus half helicity for the particle and minus is minus half helicity for the particle. So once we do that, we can just apply the crossing equation to our special case, and you get this crossing matrix, which I've displayed here. So it's a 5 by 5 matrix, and you see that the entries are some angles, and these angles are related to the Mandelstam invariant. So this is the ST crossing equation. Similarly, we can also do the SU crossing equation, and again you get some 5 by 5 matrix. And as I mentioned, this crossing matrix is going to be a function of the Mandelstam invariance.
Sorry, could you remind me how you got this matrix?
Yeah, so I had this general crossing equation here.
So the beginner, this thing.
Yeah, and then, I didn't show it here, but this is some big, huge function of these ST and U and the masses. But for the equal mass case, it simplifies, and then you just pick the value of lambda on both sides, the value of the helicities. You actually get 16 equations, but then we have these relations, so you can reduce it to 5 equations, and that you write it as a matrix.
These are the same functions that appear in the partial wave also.
Yeah.
Is there any reason? I guess the same kind of.
Yeah, it's the group. It's from group theory, right? Because
yeah.
Yeah. So this was crossing, and now I'll briefly mention kinematic singularities. So basically, to consider those, you have to go back to the definition of your one particle state. So how they are defined is that to define, say, a one particle state along the z-axis, you start with the one particle state at rest, and then you boost it along the z-axis. And this boost parameter eta, it depends on the momentum of the particle. Similarly, to go to define the particle along some angle theta, you first boost along z-axis, and then you do a rotation to make it point in the direction you want. And then the key point is that this rapidity parameter eta and the angle theta depend on the Mandelstam invariant as given here. And as you can see, this relation is not fully analytic at these special points, s equals 4, s equals 0, t and u equals 0. There are these non-analytic, there are these singularities. So this is basically the reason why you get these kinematic singularities. The details, so basically what you can do is you can isolate what kind of behavior this will lead to for the amplitude in general for any spin and any mass, but that So I won't display that here. I'll just show the result for the Majorana fermion case. And basically what happens is that at s equals 4m square, all 5 amplitudes have this pole, and the residue in fact is not independent. They are all related in this way. At s equals 0, the first 4 amplitudes are fine, but the 5th amplitude has this square root s behavior. And similarly at t and u equals 0. So now that we isolated how these amplitudes behave, we do the obvious thing, which is just make linear combinations of amplitudes which don't have this behavior. So we just multiply the first amplitude by s minus 4m square, and the first 4 amplitudes by s minus 4m squared to cancel this pole. And the 5th amplitude, we cancel the pole and also the branch cut. And we make some linear combinations of these. So basically we define these regularized amplitudes, and these matrix elements have some factors which take care of this. And these regularized amplitudes have no kinematic singularities.
Can you please repeat how did you get the universal structure of the singularities? Because you have not mentioned any specific process, right? I mean, these are
so that is a bit it's a bit involved, so that's why
okay.
Yeah, I can describe it maybe later, because I think how much time do I actually have?
Yeah, we usually are flexible with time, so we'll.
So then perhaps I can finish, and then if you're interested, I can explain how to do this.
Sure.
Okay, so this is how we define these regularized amplitude, which have no kinematic singularities.
So why do you want to take the linear combinations? Because this already you've taken care of the.
Yeah, that's true. So I'll get to that maybe in 2 slides.
Okay.
Yeah. So
sorry, could you tell me what is this regularized amplitude again? What does it denote?
Regularized amplitude is basically some linear combination of these things here, which don't have any kinematic singularities. So the amplitudes have these singularities, right? So s minus 4m squared type behavior and the square root behavior. So we just
these are some objects which don't have any singularities.
Yeah,
that's the definition.
I mean, the definition is basically this equation here and this explicit matrix.
I'm just wondering, since the residues were related, you could probably construct simpler combinations which didn't have any.
Yeah.
Right, but why multiply with s minus 4m squared at all?
You want to multiply by s minus 4m squared so that it doesn't have this pole. So we don't want this pole.
I mean, since the residues were related, right? This a1 equal to minus a2 and so on. So if you just wanted to cancel the pole,
so actually what we do is we make some combinations to cancel it, but you still need this actually. Yeah, I mean, I'll get to why exactly we chose the form we chose in a bit. Yeah.
Okay, thanks.
Yeah. So these are the regularized amplitudes, and now we assume that they satisfy Landau analyticity, which means they basically just have the cut from 4m squared. And now we use an ansatz which is similar to what was used for the scalar case. So this we map the the ST and U planes, which have this cut from 4m squared to infinity, to the interior of the disk. So the upper side of the cut goes to the upper side of the boundary, and the lower side of the cut goes to the lower side of the boundary. And then basically Landau analyticity means that these functions are all analytic in this disk, in this row variable. So we just expand it as a polynomial. And then to implement it numerically, we truncate this series at some n max. And the idea is that as you increase n max, you're giving a lot of freedom to your functions. So it basically converges to the optimal S matrix.
What is the map from S to rho?
So you mean the explicit form?
Yes. Is it complicated? Oh.
I mean, it's slightly complicated. It's like this. It's like basically, I mean, this cut is like a square root cut. So you're basically opening it up.
Okay.
The explicit form, I don't think I have it in my slides, but I can tell you if you want.
Oh, okay.
Yeah. Okay, so once you do that, so this is the ansatz for the amplitude, and this takes care of analyticity. Now we have to still impose crossing. So we know the crossing matrix for the full amplitude, which was this CS, which I showed a few slides back. From that, we can compute the crossing matrix for the regularized amplitude by just conjugating it with the matrix that takes you between the full amplitude and the regularized amplitude. And it turns out that when you compute this matrix, it's purely numerical. There is no factor, there is no dependence on SNT anymore. Similarly, you can do it for SU crossing, and you find that the crossing matrix for the regularized amplitude is purely numerical. And now I'll explain.
Is there a reason why that had to be true?
Yeah, exactly. The reason is basically this slide. It's that you can now reintroduce tensor. I mean, you can think in terms of tensor structures, which was option 1, right? So you suppose we choose this particular basis of tensor structure. So the U and V are the Dirac solutions to the Dirac equation. So they are the 4-component Dirac solutions. And you just contract them in this way. And the 5 structures are differentiated by these factors of gamma and sigma. So sigma is the commutator of gamma, and also gamma 5 and gamma phi gamma mu. So you see you have these 5 structures. And if you choose these 5 structures, then the regularized amplitudes are precisely what you would get as scalar components sitting in front of these tensor structures. So and this also explains why they're numeric, because you can, using fierce identities, you can actually cross them and then bring them back, and you get the crossing matrix numerically.
Right. Okay.
Yeah.
So all the kinematic singularity business is this this T matrix here.
Yeah, exactly. So now here they're functions of 4 momenta. Right now, if you go to the center of mass frame, you can precisely evaluate what these matrices, I mean, what they are in terms of ST and U, and you'll explicitly see these kinematic singularities. And in equations, basically what I described is the amplitude is basically, you can now just take the set tensor structures and evaluate them in the center of mass frame. And this is precisely this matrix M. So this matrix M is nothing but this tensor structures evaluated in the center of mass frame. And this is also why you were asking why we chose some linear combinations. It's so that this happens. And you can also now consider crossing. So these Dirac spinors are defined for positive energy 4 momenta. You can analytically continue them because you know their explicit form. And it turns out that, okay, you pick up a factor of 5, but helicity changes sign as you expect. And once you do that, you also get out of your ordering that we chose there. So we also have to rearrange them. And once you do that, you get this, this matrix, which is precisely the numerical crossing matrix that we found from option 2. Any questions? Or? Okay. So this takes care of crossing, because now this matrix is basically just numerical. So it's just going to be some linear constraint on that.
Sorry, I have a very stupid question. Like in the first equation, on the left hand side, you have the full your S matrix, right?
Yeah.
Or is it stripped of your kinematic singularities?
No, there are kinematic singularities on the left hand side. On the right hand side, they are in this object.
Okay. But if you go up in the TIs,
yeah,
these,
because there are some square roots here, right? When you define these, yeah.
Okay, I see.
Not only are there square roots here, when you go from P, C, or M to the ST and U, there are the singularities as I showed.
Okay, do you have the pole? Okay, square root singularities I can see, but like the pole singularities also appear on the tensor structures.
Yeah.
Okay.
I mean, you can just take it and plug it in.
Evaluate it. Yeah. Okay.
Yeah. Okay. And now unitarity, again, it's just the special case of the general prescription that I gave. So for Majorana fermions, you have 4 options for the helicities. But since they're identical, it turns out that the option where you say first particle is positive helicity and the second particle is negative helicity is the same as if you interchange, because you're just rotating them and getting a state with total angular momentum L. So there's actually only 3 options because they're identical. Moreover, we make these linear combinations so that they are parity eigenstates. So once you make these linear combinations, the first state is parity odd, the second and the third states are parity even, which means that since we assume parity invariance, there is no transition from the first state to the second and third states. So you don't have to consider the full block, you only have to consider sub-blocks. And moreover, you have selection rules for these 2 states that they only exist if spin is even, because again, they're identical particles and there are some selection rules. And here, the total spin has to be greater than the helicity difference. So this state only exists for L greater than or equal to 1, but it exists for both even and odd L. So once you have this system, we just apply the machinery that we developed, which is to consider this inner products between in and out states. So if you consider the first state and take in and out, you get these 2 partial waves. If you take the second 2 states, then you get these partial waves. And there can be a transition between the second state and the third state, and that gives you this partial wave. So here you just plug it in and you just get this. And once you have that, you get this final unitarity equations, which is that for L even, you have this positivity constraint. For L0, you have this. For L odd, you have this. And finally, there is this 2 by 2 block, which comes about because we can have transition between the second and third state. All of these comes from, so this constraint comes from the transition between the first state only. This is between the third state only, but here, yeah, you can go between second and third state, and you have this big semi-definite condition. And numerically, we impose these conditions up to some big L max, and then we check convergence in this L max. The idea is as you increase more and more the L max, it more and more constraints, so it keeps reducing your bound. And then we see how it converges with that. And these are where all the constraints that are amplitudes obey. Now you can ask what are the objectives. So the most obvious or the straightforward objective we can have is a measure of quartic coupling. And we can define that as you just take the amplitude and evaluate it at a particular point, for example, the crossing symmetric point. And at this point, the regularized amplitude must be a simultaneous eigenvector of both ST and SU crossing equation, because when you cross, it's just that's the point remains invariant. So this your amplitude must be a simultaneous eigenvector, and this totally fixes its form to be of this. This is the only common eigenvector that these 2 matrices have. And this coupling here is what we call the quartic coupling. And if you consider an interaction of this form, psi bar psi in perturbation theory, it'll just give you something of this, it'll give you something that looks exactly like this. But I want to emphasize that this definition here is non-perturbative. So here we just take the amplitude and say that it has to be of this form at this point, and this free parameter here, we define it to be the non-perturbative quartic coupling. And we can ask what is the maximum allowed value, and we get this plot. So we vary.
This is different from what you would have. You could have also asked about the Wilson coefficient, right?
Yeah, we could have also asked about the Wilson coefficient, but for right. So you're saying
at low energy, expanding this thing at low energy and looking at.
Yeah, we could have done that, but I guess for massive particles, people don't really. I mean, at least people are more interested. I mean, this is like, yeah, we didn't consider the Wilson coefficient, no, but like, guess the Wilson coefficients, for example, in the photon, that's what we are considering, yeah.
Okay, thank you.
But here, yeah, we just considered the others, yeah. So now we have these, so this lambda we defined, and we, okay, put this 32 pi to compare with some literature. And basically what we find is this plot here. So n max is the number of terms, I mean, it's a measure of the number of terms we allowed in our ansatz. So we start from 10 and go up to 26. And here this coupling is plotted as a function of inverse n max. And as you can see, as you increase n max, you're giving more and more freedom to the function. So it's getting, I mean, you're allowing more and more freedom. So the bound is getting higher and higher. But as you increase n max, it seems to become linear, and we extrapolate and we say that this point here is an estimate for the maximum value that this quartic coupling can take. So this was the upper bound. We also have the lower bound. We do the same thing. So it's around -11.
And this value should ring a bell or not?
No, I don't think this particular value has anything significant. I think it's more so yeah, one is that, okay, there is a bound, and two, there is this idea of perturbative unitarity, or also called this naive dimensional analysis, if you've heard of this, which is that where perturbation theory would break down, like basically if you have loops, then you want that this value should, so when you have loop corrections, you get basically lambda over something like 16 pi or 32 pi, right?
Mm-hmm.
And so based on that, they expect that this should be of order 1. So at least it's compatible with that, but I don't think the specific value has anything significant to it.
But this is an optimal bound, right? I mean, you would expect this to be optimal, or?
No, as I was saying, we don't impose, for example, elastic unitarity and things like that, right? So you would expect, in fact, actual bound to be maybe sharper.
I see. Okay.
Yeah. And that was the quartic coupling.
Yeah. Sorry, this is what was this?
This is the quartic coupling, but the lower bound. So that was the upper bound, so maximum it can take, and this is the minimum.
Can you remind what bounds you have got for the scalar case?
For the scalar case, I think, I mean, this was not done in our paper, but I think it was comparable to these bounds, yes.
Mm. Yeah. Thank you.
Yeah. Okay, so that was the quartic coupling. But now we can also consider Yukawa coupling, by which I mean we have a scalar bound state, and we look at the coupling of our Majorana fermions to the scalar bound state. And what do you mean by a scalar bound state is just that we have a pole in the spin zero partial waves.
Sorry, so when you do this previous analysis, are you assuming absence of bound states or something, or?
Yeah, we are assuming absence of bound state, but I think even if you put a bound state, it doesn't change it.
It doesn't change.
Yeah.
Okay.
Yeah. So now we can add a bound state, and by which we mean scalar bound state, by which we mean a pole in the spin zero partial waves. And basically the idea is as follows: we add a pole to our regularized amplitude, and then we require that it only contributes to the spin zero partial waves, and you impose crossing symmetry. Then basically it leads to only two solutions. So the first possibility is the scalar bound state, and it has to be of this form in the regularized amplitude. So this form is fixed up to some coefficient, which is basically the coupling. So we define this to be the non-perturbative Yukawa coupling. And again, if you put a Lagrangian interaction of the Yukawa form, then you would get precisely this structure. And now you can plot this coupling as a function of the mass. So this capital M is the mass of the bound state. So you can plot this coupling as a function of the mass. And these are for various values of n max. And convergence is not that great in this plot. So actually, if you extrapolate, you see that there is a big gap. And right now basically this is the way what we are doing right now is called primal optimization. So we are trying to see what is the space of allowed theories. There's a dual formulation of this problem called, so what it does is it disallows disallows the space of theories. So it says, okay, some value here is not allowed and so on. And in 4D, there was recently a paper which did this for scalar particles. So for future work, possibly we can have a dual formulation of the spinning case, and then maybe we can get some bounds coming from the other side so that we can sandwich, because here it seems that convergence is hard. And similarly, as I was saying, there are two solutions. The second solution corresponds to a parity odd spin zero bound state, and that's what we call the pseudo scalar. And okay, it has some other form, and again there is a coupling. And if you have this phi psi bar gamma phi psi bar, so this is the pseudo scalar. So phi bar here would be pseudo scalar. You get precisely this form.
Sorry, when you say regular here, you mean it can have cuts and so on, right? At 4m square.
No, what I'm saying is that this H, so we have two kinds of amplitudes, right? The T amplitudes and the H amplitudes. Like the regularized amplitudes and the full amplitudes, like the center of mass frame amplitudes. I'm just saying that this form is only true for the regularized amplitudes. If you want to see what it looks like in the full amplitude, you have to multiply it by the matrix.
I understand, but the full. But even the regularized amplitude has dynamical cuts, right?
Yeah, it has the 4m square cut, yeah.
But here you are not writing that. The regular means there is a cut also.
Yeah, so this, so it's okay. This is a bit of so regular means it's also the cut. I meant regular in this row variable. So in the disk, it's regular.
Oh, I see. Okay.
Yeah, but it has the 4m square cut. Yeah. So then you can also plot this bounds for the pseudo-scalar coupling. And you see that at least at the threshold, this coupling goes to 0. And there you can do some non-relativistic approximation and try to get some bound. And this dark black line here is, the black line here is the bound, the non-relativistic bound. And okay, it seems to at least match that near 4m squared. So yeah, these were the bounds that we found. And
question. So this is really bound on G or G squared?
The bound we put is on G squared. So actually this should be modulus of G. Yeah, you're right.
I see. And then why should I expect that above certain mass that there should not be coupling? That this is going to 0, right?
So here it goes to 0, that you can see from, so for example, in the previous plot, it didn't go to 0. But right. We stopped here because after this point, it's no longer a bound state, right? It's going to be an unstable state, like a resonance.
Right.
Because now it can decay. So it's no longer a pole on the real line. It's going to be a pole in the second sheet, which we don't parameterize.
I see. Okay.
Yeah.
Okay.
So that's why we stop at 4m squared. Yeah. And now why it goes to 0 here is, okay, if you do some non-relativistic approximation, it turns out that it has to go to 0 here.
Okay, thank you.
Yeah. As in, it has to go to 0 in some particular rate, and it seems that the rate matches. Okay, so for the conclusion, so we basically reviewed and set up the formalism to bootstrap scattering of particles with any spin. And we applied it to Majorana fermions and estimated some bounds for the quartic coupling and the Yukawa and pseudo-Yukawa couplings. So for the future, one thing is these photon-photon scattering. So that is work in progress. And also, I think the group at TIFR also had this nice work about all these tensor structures. So we're actually using that, and also this formalism of the center of mass frame amplitudes. And indeed, the idea would be to bound these Wilson coefficients. Other things that we can consider is, say, pion-nucleon scattering, which is going to be a much richer system, because now you also have a global symmetry, which is the isospin symmetry. And you have now multiple processes, because you can't just consider pion-nucleon, because when you consider scattering, I mean, when you consider the cross process, you also have pion-pion going to nucleon-nucleon bar. And now when you consider intermediate states, you also have like nucleon-nucleon going to nucleon-nucleon bar. So you actually get a system with many different types of amplitudes. But the fruit of all this labor would be that there is a bound state near threshold called the deuteron. And there are some experimental data. There is some experimental data about its coupling and so on. So we can try to see what Bootstrap says about it and see if how close it is to the boundary. Other possible future directions are glue ball scattering. So there are like spin 2 glue balls and so on. So we could consider them. And finally, as I was mentioning, what we are doing is this primal approach. So we look at what is the allowed S matrix. So everything we have, we basically explicitly construct an S matrix that satisfies all constraints. The other side of this, so is that you can then consider this dual formulation, which says this region is not allowed. This is basically how, I mean, this is the spirit in conformal field theory, where you rule out theory space. And till now, this dual formulation was only there for the 2D case. For 4D, it was only recently done in this paper by Hay and Krushansky 2 weeks back. And in fact, if anyone is interested, I think there's going to be a talk on this in the Bootstrap seminar on Wednesday. So now it would be nice to do this for spinning particles also, because it seems that convergence is also better in this dual formulation. Yeah, so I think that's it, and thank you for your attention.
Thank you very much, Aditya, for a wonderful and very clear talk. Let's all unmute and thank. Okay, so we have had many questions during the talk, but if there are more questions, yes.
Just to ask, this dual formulation, this thing that you mentioned, there have been a recent series of papers by Rasteli and Simon Karam who
yeah, so those are also dual formulations, but let me see. So first of all, the first ones were only for forward scattering, so they were only at t equals 0.
Correct.
Then there was, I think they also considered expanding around t equals 0, at least in Simon's paper. But then you see that that doesn't work if you are considering loops non-perturbatively. So here it is non-perturbative.
Okay.
Yeah, so that's the.
And just curious, like so in your numerics, what sort of computation power did you need?
So for example, I think, so let me see. You have to first of all use a cluster, and to get, say, like for nmax equals 24, I think you have to do it for like on some 28 core cluster, I mean like a node, you have to do it for like 24 hours or like multiple sessions of 24 hours.
Okay.
For each point.
Okay. For each point. Okay. Wow.
I mean, here so for example, suppose you just consider this maximizing lambda. So for this one point here, so we fix, say, L max, so which is the maximum number of partial waves, to say 46, and we fixed n max to 26. To get this one point, you'd have to do it for like 24 hours. So you have to send one job to the cluster, and it'll last like, I think it actually lasts 2 sessions, so around 40 hours or something like that. Yeah.
Okay.
Yeah. So it's, I mean, quite intensive numerically. So it's very hard to push it further, for example. So that's why you stop here, not because we. Yeah.
So one question, this Nimar Kanihamed, Yutin Huang and collaborators, they wrote a paper called EFT Hedra, right? EFT
yeah.
Hedra.
Yeah.
There also they have a similar, they consider a similar kind of thing, right? Where they look at, I mean, at least the formulation of the problem is similar. So
yeah, but again, I think there also they don't consider loops, right? At least, so you can get one side, like you can get the bounds at forward scattering. So so one set of bounds you can just get by saying consider the amplitude at t equals 0, and then you just use the fact that imaginary part of the amplitude should be positive, and that gives you some bound. But if you want to get two-sided bounds, as far as I know, you have to expand at t. You expand around t equals 0, either as like just normal polynomials. That's what Simon does, and compares like different orders in T. Or in Nima's paper, I believe they consider like an expansion in these Legendre polynomials, and then again they consider different like positivity of this Legendre polynomials, and then they use that. But again, here basically the assumption in their work is that they neglect the loops in the effective field theory, but they don't neglect the loops in the stuff that they integrated out.
Right.
But here we don't do, I mean, we just doing it numerically, so we don't make any such assumptions.
Great.
Like for examples in the photons, that is what we are doing. So we can, so all those works were for, I mean, okay, Nima and his collaborators also had some bounds for photons, but they had, I believe, only for like, so there is the f to the 4. There are two types of operators, right, in 4D, like the independent ones. But I think their bounds only come at the next order, like for del square acting on f to the 4. So, but you can still use this argument in these types of papers, like Ricardo's and his collaborators' papers or Simon's papers, to get some analytic bounds on these f to the 4 operators, like the Wilson coefficients. And now we are just going to start the numerics, and we want to see if numerics actually gives us stronger bounds, or it's just the same, and these are actually already quite strong. So that's one thing we're going to do. And I was hoping I'd have some plots to show from that, but yeah, I think we're just starting the numerics. So maybe in a couple of months I'll have that.
But in this case, in what you are doing also, you are assuming that the massive things that you are scattering are lightest, right?
Yeah, I'm assuming they're lightest, yes.
So in particular, you don't have a massless exchange, which is what causes all the issues in their case, right?
No, in their case, they're considering massless particles, but
no, their cuts start from a particular after a mass cap, right?
Oh,
yeah, that's because that's what. So they consider tree level in the effective field theory, but loops in the theory that they integrated out. So suppose you integrate it out at some mass m, you could have loops that after this mass m, so you have some cut starting there. And in your effective field theory, if you considered loops, indeed the cut would start already at x equals 0, right? Yeah.
Right.
So for photons, you are looking at cuts starting from 0 or some
cut starting from 0, yeah. So indeed that
effective field theory loops, EFT loops,
right.
Not.
Yeah, for the photons, we just do it non-perturbatively as is. So the cut starts from s equals 0. We don't make any assumptions about whether effective field theory is weak or not. So yeah.
Okay. Any more questions?
Sorry, what is the sense of n max? N max. What is n max really?
Yeah, so n max. So I think maybe I was fast there. Is let me see. So here, these amplitudes we are mapping to this this disk, right? So the S plane minus the cuts we are mapping to the interior of the disk, and then the idea is that it's regular inside the disk, so we can make a polynomial expansion there. And now we have, it's like an infinite series, but we can't put that on a computer, so we truncate it at some n max. And now as you increase n max, you're allowing more and more in your series, and we hope that it converges better to the optimal S matrix. Yeah. So this
Thank you.
N max, yeah.
Okay, if there are no further questions, let's thank Aditya again for a wonderful talk. Thank you.
Yeah, thank you.